Welcome to Startup School. Can you believe it? The fifth week is almost over. We have only three classes left, including this one, this week's Thursday's class. My name is Timon. I'm a go-to-market manager in Google for Startups, and I'm your host and MC today, inviting to a very interesting class on tuning and reinforced learning from human factor, a very long acronym, but this is a very important technique in machine learning and tuning your models. So we're going to learn today a lot about models. We have a fantastic instructor that will give us a huge overview on how to tune and possibly learn from human feedback and teach your model to be the best and the one that really solves your challenges. But before that, I want to just give a quick reminder. I know most of you already know it, but our structure, easy, very easy. We have a live sessions that are available to watch on demand. We have code labs and notebooks. And for a few of the code labs, you can get a skill badge on our Skills Boost platform. I know most of you already have the Skills Boost platform access and the credits that we are giving, but just in case you are new here, remember to redeem your code to Skills Boost and your credits soon, because the unique URLs that were distributed with you have some expiry date. So make sure that before the end of the startup school, you get the access over there. All the labs and also these labs and notebooks that will be covered today are available on our one and only repository, Google/GenAI-Labs. I can't express it more that these live sessions, and I'm happy to have you live here today, are the perfect opportunity to ask your questions to our moderators, our experts, to our AI developer advocates. They are today ready for you with the Q&A session. Right there below the screen, you have the QA button. You should know the drill. You post your question, and in a couple of minutes, some AI expert from Google will answer your question. At the end of the session, we're gonna talk together with Catherine about your questions. So make sure you upvote those that are the most interesting. These sessions are recorded, as you know, and available on this very platform to watch on demand. So for all of those of you who watch it on demand, hello, welcome. We're not sharing the slides. You have all the labs and notebooks in one place, but don't rush right now or rush when Catherine is covering the notebooks. You can complete them on your own in your free time. With that, all that is left to me is to invite Catherine to the virtual stage. Catherine, welcome. I'm very happy to have you here. Lovely afternoon, I guess, over there in Singapore. Here in Warsaw, it's just a bright early morning. Happy to have you here. I wish you good luck on tuning and reinforced learning from human feedback. That's a very long one. I'm thrilled to have you, and I'm going to listen very carefully to your session. It's a very interesting one. We're going to see each other in about an hour for this live Q&A. And with that, the floor is yours. And once again, happy to have you here.
Thank you. I hope everyone can see my screen. And yeah, let me know if there's nothing like my audio or my video is not working. I want to keep my video like on during the session, but if my internet is not working, then I might be turning off my camera, but I'm here with you all the time, okay? So hi everyone, welcome to today's Startup School session. My name is Catherine Wang. I'm the APAC Solution Lead for Generative AI at Google Cloud. So during today's session, we will be exploring what are some of the options to tune foundation models, and especially drill down to RLHF, a very long name, reinforcement learning with human feedback. And just a bit of intro of myself. My background is in computer science and applying statistics. I've done 1 or 2 years of research at Stanford on NLP and reinforcement learning. I was an ex-KPMG and ex-Microsoft. So now my main focus on Google is to support Google Cloud's APAC priority customer in adopting and building Gen AI solution at scale. So here is today's agenda. We will be covering some fundamental concept of model tuning. It is now week 5, so I'm assuming everyone is already familiar with all the fundamental concepts of large language models, so I won't be spending too much time in here. And then I will listing some of the options to tune the foundation model. And I will briefly mention adapt tuning and distillation, which is the key functionality we are offering from Google Cloud Platform on helping you to tune foundation model. Then we'll be diving into reinforcement learning with human feedback. The concept is very tricky to understand because there is a lot of theoretical concept around how to run this pipeline. I will be explaining it. Hopefully you can understand what we're trying to do in here. And lastly, I will be showing you how you can actually build a reinforcement learning pipeline in Vertex AI. So we know, we have different ways of tuning, but why do we want to tune a foundation model, right? We have all experienced with foundation model, BARD, and you might notice that a single powerful vanilla model can perform on all sorts of tasks on, just one interface. But depending on what you want to do or how you are formulating your prompt, you can ask the large language model to brainstorm, help me to write an essay, or inspire me to write some bullet points of my, a newsletter, right? Or you can ask the large language model to do classification, give a few categories and ask the model to classify one, content into one category. Or you can ask the large language model to extract key information from a long document, or ask the large language model to summarize a really long document. Lastly, with the new release of Gemini Pro, if we go to BARD, you might notice that BARD can not only understanding text, but also image or something in combine. You can give BARD an image and then ask the BARD to generate something based on your instruction, aka prompt, and the information from that image. The result can be both in text or an image format. However, depending on what you're trying to do, you will soon hit the limit of prompt design. Small changes in wording or even word order can largely impact the model's output. And you might be trying a lot of prompting techniques. You might be using few short learning or chain of thought, and that will end up eating a lot of model input context window. And when we are making the API call or the prediction, the cost of one particular API call is not by call, but by the token input limits. So if the longer the prompt, the more cost of your one particular call will end up being. Again, with a lot of tries and error, it does not guarantee you will be getting a very consistent result. The reason is we will be keep releasing and updating the model. Let's say if you build a really good prompt for one checkpoint of the model, let's say ChatBison 001, and over the night we made a release of the model image, and you might be seeing slight variance in getting the result. Hence, we want to try something other than just doing prompt design, right? So if you know this, task-specific tuning in large language model, this is not a new concept. Many people have tried this, but this is actually the way to bring in your own domain data, your enterprise knowledge into the large language model to build a specific model just for yourself. So what is foundational model tuning? At Google Cloud, we have been working with our customer and the community to understand what is required to tune your foundation model. Apart from prompt design, we offer adapt tuning, we offer reinforcement learning with human feedback, we offer distillation, and we also offer full fine-tuning on open source dataset. So largely speaking, if you think of tuning a model, it comes with three distinct methods. If you're working with transfer learning before, you might be already familiar with the concept of full fine-tuning. Here, full fine-tuning doesn't mean that you will be building the model from the scratch. Nobody, like apart from the large players on the market like Meta, Google, or Microsoft, no one, like smaller company, are not necessarily rebuilding the foundation model from the scratch. What will happen is you are taking a frozen layer or frozen weight from the foundation model that's trained by this large company, and you will be doing domain adapter tuning, aka full fine tuning, not full fine training. That's the caveat in here to further align the foundation model to your specific domain knowledge. And the second part is adapter tuning. So adapter tuning is just to update a small set of weights. That small set of weight can be embedded into the model, or a completely new set of new parameters that you want to add on top of your model to make your model aware of the contextual information or the knowledge you are bringing in. Distillation works in many different ways. Distillation, at the beginning, it was used to reduce the model size. Let's say you already trained or tuned a foundation model, and you deployed this model on an endpoint. However, there is a requirement to have the same capability on your mobile device, and you are building a mobile application. In this case, you probably don't have enough computational power on your mobile device, and you still want the model to perform pretty similar to the original model. That's why we are having these techniques to distill the knowledge of the larger model to a smaller model. So you can keep the same consistency, keep the same performance on both the teacher model and the student model. Here is a more granular view from Google Cloud's perspective. We have prompt design. In prompt design, you don't really need to have a lot of ML expertise, but you do need to know how to write your prompt, right? You might end up trying a lot of different things to come up with the best prompt, and you might be giving the large language model a few examples like few-shot learning, or you decompose your prompt into step-by-step reasoning type of templates, and that will give you a much better result. The second part is adapter tuning. In here, we load the frozen weights from the pre-trained model, and we are focusing on building the adapt layer. You just need to have a few hundreds of thousands of labeled data sets. Pay attention in here. You need to have labeled examples in order to do this adapter tuning. The same case applies to distillation. Both tuning method requires you to have a ground truth or golden data set to produce a meaningful tuning. And reinforcement learning with human feedback, on the contrary, it is more suitable for when you are expecting a more creative response. Let's say if I want the model to write an essay or to write a newsletter, there is no one single best answer, right? So I can only have the human preference, which is I like this style better than the other one. So in this way, I am giving you the pairwise, thumb up, thumb down, or score for the model to learn the preference of human. Lastly, we offer full fine-tuning, which requires a massive amount of both unlabeled and labeled dataset, and a lot of computational power, GPU, TPU, to even start training this model. Think of Llama 2. I think it has few trillions of token or parameters to load that model in memory and kick off the training or tuning is a really computational expensive task. Let's look at adapt tuning and distillation. So here is the concept. And this phrase has been misused many times. The adapt tuning and distillation are all subcategories of supervised fine-tuning. Supervised fine-tuning is not a new concept in machine learning, right? It's the same way as you are preparing your training data set for any ML models. Supervised fine-tuning in large language model is requiring you to have the prompt and the expected output. As you might see, since I'm requiring the expected output as part of the training dataset, you do need to be aware that this expected output need to define the exact outcome you want the model to produce, right? The style, the key information, the structure of the output, etc., etc. So adaptive tuning is to train a small subset of parameters in the foundation model. That's one way, or it can be, a completely new set of parameters, as I mentioned before. It really depending on which method you are using. There is no one single best method to go for. The state of the art for the optimal techniques seems to be changing all the time. If you are really interested in this area, you can follow some of the research paper, and they will be discussing some of the theoretical method in doing this adaptive tuning, like how much parameters you should be tuning, how many data, and which layer you need to specifically tune, or which area you will be adding those additional parameters to make the model aware of the extra contextual information. So regardless of the specific methodology, here is some big benefits of the adaptive tuning. It is much faster, right? It requires much smaller data sets to tune, and it requires less computational resources to tune. The adapt tuning can also make solving of the model much simpler, because we are not touching the frozen weights. And what will end up happening is when you are doing the inference, and the adapt layer, which is the extra parameters, will be loaded on the fly when you are making a call to your custom model. And since the layer is so light, and the method of how we are injecting those extra information into the foundation model is very smart. That makes this loading of the additional layer look like you can hardly notice the latency of loading that extra information. So that's how this adaptive tuning really works. This is some of the example of how you should be preparing the data set for the supervised fine-tuning. The key point in here is you need to follow the exact prompt style or the exact output structure you are requiring the model to produce. Sometimes when some of my customer is preparing the training data set, they forgot to prepare or put the instruction, the full instruction into the input. That end up, making the model a bit confused when you are putting this tuned model in the wild, and your customer, your user, is prompting the model in a different way. Then you might be getting a inconsistent result. But one point I want to also mention in here is supervised fine-tuning is a really good use when you want to take your data in one format and convert it into another format. Let's say you are taking a conversational dialogue and you want to just remove all the PII data, or you are taking a unstructured description of a clothing items and you want to convert it into a structured JSON so you can do some further analysis, or you are extracting certain relevant information from a user request or a complaint. Those very deterministic type of task are a perfect use case of supervised fine-tuning, aka building the adapt layer. Here is a very, very high-level overview of how the supervised fine-tuning, adapt tuning really works in Vertex AI. I hope you can see my mouth. So at the beginning, we are loading the frozen foundation model weights from the shared instance provided by Google Cloud. And you are also uploading your own data sets. Those data sets will be kept on your own project, on your own premise. And you will be giving those as the two inputs to the training job. During the training job, you define the learning rates, you define the batch, you define, how much, which compute resources you want to use, and then the tuning job will be kicking off a Vertex pipeline. So the Vertex pipeline is an abstraction built on top of Kubeflow pipeline. It removes a lot of technical overhead, and we are also offering you a lot of pipeline template to help you even simplify the whole tuning process. You just need to bring in your own dataset, specifying which frozen weight or which model checkpoint you want to use as the input, kick off the pipeline, kick off the tuning, and then once the tuning is finished, your adapt layer will be saved in your own project, in your own premise. That's your own knowledge. Google doesn't have any information of your adapt layer. And the model that you have tuned can be also deployed and put into the model registry. That's the image. During the inference process, we will be again loading the frozen foundation model weight that you choose at the beginning to input in your tuning pipeline, and load the additional layer. This loading will be hardly noticed by anyone. It is instant, and your new prediction will be going through these foundational weights, plus the additional adapt layer knowledge, and producing the output. The model endpoint will be deployed on the Vertex endpoint. It is real time, and it is really good for you to use in real time and at scale. Right. So here are some high-level recommendations from Google of how you should be configuring your tuning job. But I just want you to remember that this whole field is very empirical, meaning that it is learned from trials and errors. There is no one single golden rules to tune your model, even though we are giving you some guidance on classification, summarization, extraction. You do need to customize it or try it yourself and find the best way, the best configuration to tune your specific model. The next big question of the large language model is the inference cost. Anyone who have tried to deploy the large model in real time might notice it's not cheap. So we have three ways of reducing this cost. Quantization is one way. It is simply replacing the model's high precision number, like 32 bits float, into a low precision one, like 8-bit integer. This makes the model much smaller. However, you need to sacrifice in accuracy. Actually, all the ways to reduce the model size, to reduce the inference costs, are at a certain point sacrificing the accuracy. It is the trade-off of high accuracy versus the cost, right? Pooring is removing less important weights. It's the same concept as you use to trimming, any extra branches in the tree model. And lastly, we have distillation. As briefly mentioned before, it is the concept of using a larger teacher model to transfer knowledge to a smaller student model. So for distillation, I just want to explain a little bit more. To dive in here, as you can see in the diagram, you can use few shorts data to kick off the training, or you can use many shorts data. There is no golden rules in here. It really depends on what you want to do, right? What type of task you ask the teacher model to perform. And the distillation knowledge then will be transferred into the student model, and the student model will be using the distillation knowledge and also the same training data set to learn from both sides, to be aware of the teacher's behavior and also what's going to happen in the wild. Here is a more behind the thing look of what's exactly happening in distillation, distillation, right? So let me just explain the key components in here. First is the distillation dataset. It is the training dataset fed into both teacher model and the student model. This can be the same dataset for the teacher model that has been originally trained, or it can be a completely new set of data. As I mentioned, you choose you choose what type of data you want to use to tune on a particular task, right? Summarization, extraction, classification. And in here, the teacher model will be producing the soft label based on the distillation dataset. Why we need to have a soft label? Soft label means that instead of giving you one true answer, I'm giving you the predictions and probability distribution of all the possible output. Let's say in this particular sentiment analysis, instead of positive or negative, I'm giving you 70% positive sentiment and 30% negative sentiment. In this more granular view, I'm actually seeing how the teacher model is making the decision, right? So I'm asking the student model to produce the same soft label. And I will be able to compare both soft label from the teacher model and the student model to further align and ask the student model to learn the behavior from the teacher model, not just the answer, right? After the student model align with the behavior of the teacher model, I will ask the student model again to produce a hard label. Here, the hard label is just one single class, let's say positive sentiment from the input data. And in here, I will be comparing the one hard label to the true label, so I can again get a cross entropy loss where I can keep optimizing it to further align the behavior to the true label dataset. So we are optimizing both distillation loss, which transfer the knowledge from the teacher to the students, and then further testing or align the student model to the true label. I hope that's a good explanation. So before I'm jumping into reinforcement learning with human feedback, I want to just show you quickly how you can run the tuning pipeline inside of Google Cloud Console. Right. So I hope you are all familiar with this one. So this is Vertex AI, our end-to-end AI ML platform for you to do not only traditional machine learning ML ops pipeline, but also generative AI. You can see we have multimodal modality, we have language, vision, speech, but normally I will always start with Model Garden. It is the one place you can view all the model that is offered by Google Cloud, including our proprietary Gemini Pro Vision, which is the multimodal, and some really famous open source model like Llama or Claude. Let's go to Llama. So in here, you have a few ways of doing the tuning. So you can either deploy Llama as it is on the model endpoint as the model endpoint, or you can open the notebook. If you choose the notebook, there are a few options in here. You can do the direct deployment or perf fine-tuning. Perf fine-tuning is actually, building the adapter layer, or you can do RLHF tuning. Those are all the examples that is available for you to try quantization or evaluation. And if you don't want to open a notebook, if you want to just run the fine-tuning pipeline, you have an option in here. Those are the pipeline template I just mentioned. If you click this one, it will bring you to the pipeline template that we prepared for you. As you can see, it is all pre-built. It will help you to validate your pipeline, and it will help you to create a TensorBoard instance if you want to track the performance of the model, compose the parameters for the language model tuning, embed your input into vectors, and then kicking off the model tuning. In order to run this, you just need to simply input few, as I mentioned, which model you want to choose, the runtime configuration, the base model you are choosing, and the base model URL. You need to download the model into your cloud storage, preparing your output directory, and preparing your input data. And that's pretty much it. You just need to fill in those information. You can kick off the tuning pipeline. However, let's maybe jump into one of the notebook. I think you will have access of this notebook in the GitHub repo that we are providing it to you. It's fairly standard. There's not much, like the only thing I want to show you in here is if we skip all this configuration setup, authentication, and if you so in here, one thing I do want to mention is setting up the service account. You do need to grant your service account the role to read and create object in your storage, and you also need to give your service account the role and the ability to create metadata store. So all the information you can find from the Google Cloud documentation. So once you have all this and you load the pre-trained model in here, I highly recommend you to just try from the TextBython 001. Even though it is not the latest model, as the experiment start with a smaller model, it will help you to reduce a lot of cost, right? In here, we do have a few options for you to configure the model for the tuning evaluation spec and also for the actual training steps. At the moment, I don't think the tuned model location is only supported in US. We will be announcing new regional residency on the tuned model location and also on the GPU TPU location. So just stay tuned for those announcements. But if you just run this model as if you just run this notebook as it is, it will help you to pretty much like build the same pipeline and run the tuning job. Let me just open one of my tuned job in here. So this is one of the tuning pipeline I've run. Oops. And as you can see, this is a visualization of of how the pipeline has been run. In here, we have the tuned graph, and then we have the deployment graph. So the deployment graph, it's optional, but I highly recommend you to have this tuned graph. It is pre-built, but if you remove this part, the pipeline still works. It's all fine. Inside of the tuning pipeline, you can see the dataset encoder, which will encode all your prompt and all your response will be done by you, and you can check the encoded dataset. One interesting thing I want to show you is in here. So the validation part, the validation of your input prompt, we're actually using the responsible AI and framework to show exactly what are the risks or some of the issue in your prompting data. It will help you to understand if there is anything violence or harm information inside of your training pipeline, right? And once we've done all this evaluation, we check all the responsible AI or safety filter, then you can kick off the training. And you can view the TensorBoard metrics if you want to track how well your model converge. Then you can do that. And the safe model checkpoint is in here. You can also expose it, or you can simply follow the step of deploying that model in the model endpoint. Right. So this is creating the endpoint. Once the endpoint has been created, then you can simply go there. The endpoint source name, you can just click and go to that particular endpoint. Right. So just be aware of the time. Let me just quickly show you the distillation as well. So in the distillation, in this particular notebook, I'm using the same training dataset. So it doesn't really matter because the format of the tuning dataset should be the same. It's supervised fine-tuning again. You just need to provide the prompt and the expected result in here. And the setup is also pretty similar. We need to set up your project, we need to specify the region, and we need to authenticate the user. And once again, we create a new training dataset, move that into the cloud storage, and then we are, this is just some example of the input text, as you can see in here, questions, context, and then the answer. It's fairly long, and it is also good to have, the responsible AI check, because sometimes when you are gathering all this information, you might not have the ability to read through all the training data to make sure that you are not including harmful information in the training process. Then import the library. The only thing I would say that is different from the perf tuning is the method, right? So in here, I'm setting up the tuning evaluation spec, pretty much the same. I'm giving the evaluation data set, the intervals, and when I'm calling the model to tune, instead of tuning that you have seen on the other notebook, I'm asking it to distill from the teacher model. Whereas the teacher model, in here, I'm defining the teacher model as text Python, text unicorn 001. At the moment, we are only supporting text unicorn 001 as the teacher model, and text Python 001 or text Python 002 as the student model. Feel free to experiment if you want to bring another model. You might be bumping into a few small errors in the Kubeflow pipeline, but you can debug it if you feel comfortable, right? Once you define all this and you define the deploy name, acceleration, it's fairly standard. Spin up the pipeline, and you can again see the entire pipeline in the pipeline part. Sorry, I forgot to show this one. So in the tool, in the pipeline, and you search for that particular pipeline name. that you have defined in your training code. In here, it's fairly complicated, but as you can see, creating this pipeline is just a few lines of code. The mechanism behind this thing is fairly complicated. We have a data graph. In this data graph, we're doing a lot of like pre-checking. We're doing encodings for you. We're preparing the label in the right format. And then we're hitting the training graph. In this training graph, we will have the TensorBoard metrics, and then we will have the condition branches. Inside of the condition branches, you might be seeing that the tuning graph, we are kicking off the multiple pipeline prompting training, and then we're composed parameters for the model, and you can see the saved model in here. So be aware that all the model that has been saved is in your cloud bucket that you defined at the beginning. All this information is also available inside of the metadata store. If you want to build a monitoring metrics, report on those data, you can get the information in here. Right. Let me see if there's anything I want to cover. It's pretty standard to deploy graph in here. And once you deploy all this model, it's very easy for you to find all the deployed model in the model registry. Be aware that you might be changing the region. So all this model, including the imported one or the trained one, are all deployed in here. Right. Let's move back to the presentation. I hope that gives you an overview of how this very complicated concept has been translated into just a very simple implementation of the code or inside of the Google Cloud Platform. So RLHF, again, this is not a new concept, but I think at the moment, at this time, Google Cloud is probably one of the few platforms that is offering you the reinforcement learning with human feedback capability. We announced this capability in 2023 Google I/O. The key point of this fine-tuning is you can improve the performance of your model without increasing the overall size. The adapt tuning or building the adapt layer does means that you are making your model bigger because you are creating additional sets of parameters. Whereas in the reinforcement learning, you're not. It's the same model. We're just tweaking some of the parameters in a very subtle way. And in this diagram, you are seeing three different models. So at the beginning, we have the original model. It is the base model. This is the large language model. It can be BERT, it can be Llama, it can be Text Python or Gemini. And then you are bringing a lot of unlabeled input data into the tuning pipeline. And the second part is we will be training a reward model. Here, the reward model is a separate model from your base model. It can be the same model, but normally we are putting a smaller model as the reward model, because the key goal for this reward model is to learn from the human feedback, and then it will produce one final reward score for the original model to learn the human preference. So the original model can update its weight then to further align the result to the human preference. Finally, we will be saving the tuned model as the tuned large language model checkpoints. So we have, again, I just want to re-emphasize, we have three different models in this diagram. Normally, the reward model is a separate model from the original model. And in here, I'm just giving you one option using human thumb up or thumb down as the method to tune this reward model. But we do have other techniques like RLAIF, meaning that we're not using a human agent, but using a constitutional AI agent to provide feedback. So we're asking one large language model to send the reward of the other model. Or it can be simply using Blue or Raj School to train your reward model. There are a few techniques or variation of how you should be training your reward model. So the big issue, like why we want to use reinforcement learning, right? So the big issue is the misalignment, where we are expecting a more nuanced result from the large language model. For example, you're building a chatbot. The chatbot is giving user correct information, factual-based information, but that's not enough. You want your chatbot to have a personality or talk in a certain style or a certain way. Or in other use cases, we are expecting a less deterministic answer. There is no one good answer. I want the model to be creative, the model to generate more response, but I just want to make sure that the creativity does align to the human preference, right? As you can see the example in here, human preference can be expressed as thumb up or thumb down. If you want to customize the model, let's say if you want to customize the model in the case that you know the ground truth or human demonstration, then it's no-brainer. You should be choosing supervised fine-tuning. Supervised fine-tuning, because we have the target, supervised fine-tuning will always give you a better result because we know the target. It's easier to optimize the loss function. It's easy to define the loss function so we can keep aligning your model in a particular way. But for the most case, we don't have the perfect answer or lacking of the labeled data set, then we need to use human to set the preference as the signal to train the model. Now, the bigger question is how we can incorporate those human preference back to our model, right? Before jumping into RLHF, I just want to refreshing some of the key concepts of reinforcement learning. So inside of reinforcement learning, we have something called the agent. So the agent is the model that we want to train. The agent will be learning how to resolve a task by interacting in an environment that we define. The agent will be taking an action and it will change the state in the environment, and the environment will be also giving the agent a reward. Normally, the reward will be expressed as one single score to let the agent know whether or not that particular action is beneficial or not. And when I'm sending a lot of signal back to the agent will know how beneficial is each step and then accumulatively optimize for a longer term goal. So this is a very typical try by error learning. Nobody is telling the agent what to do, right? It might be oscillating or it might be exploring the environment in all directions and slowly build its own trajectory to the optimal solution. Here is the key concept, right? So taking that and putting that inside of large language model, we're applying the same principle to incorporate human preference data into the tuning pipeline. Again, we have the agent, we have the environment. However, think agent and environment as the high-level concept. It's not the name. The name doesn't matter. We describe it in all different ways. But here are the concept of the agent. Here are the concept of the environment. In the large language model sense, we define the language model, the base model, as the agent. And in expression, we're defining it as the policy. If you see policy optimization, if you see agent optimization, it all means the same thing. That's the foundation model, that's the base model that we want to train. And the second part is the environment. In the environment, we are defining the reward model. The reward model is the environment, and the extra context is the human preference data that we are giving this reward model. So what's going to happen if the policy, the agent, will be producing response, and the reward model will be getting the response produced by the foundation, the base model, and making a judgment or generating a score based on the human preference and sending the score signal back to the policy model, to the base model. So the base model can keep optimizing. So we define the reward model as a sophisticated parameterized policy. We use gradient descent to keep updating the parameters. You might be hearing techniques as PPO or PMP. Those are all the techniques that we are applying to make sure that the reward model can converge really fast, because we don't want the agent to be oscillating or going into different ways, and we want the reward model to quickly learn the preference from the human and telling the policy, which is the base language model, where to align its output, right? I hope I'm not confusing you. And here is a further breakdown of the process I mentioned before, right? That's in reality how our pipeline is implemented, right? So the core of the reinforcement learning pipeline is the RL-based language model fine-tuning process. In this process, we will be there are three inputs, right? So the first input is the base model that you are choosing. You need to choose the original large language model as the starting point. And then you need to give the model a set of prompts. Also, the model needs to know the reward score from the reward model. Once it has the three information, the signals, the base model, and the prompt example, then it will kick off the fine-tuning process to produce a fine-tuned large language model. That's the core part. However, the missing part is how we are getting the reward model or the reward score. That comes to the second part of building the reward model. In this part, we are getting the deterministic score by training this reward model. In the reward model training process, again, you can choose to load the same large language model as the base model you are seeing in here, but generally speaking, we will be choosing a much smaller regression model because we need to have a single score produced by this model to kick off the training. So the input of this particular training is the prompt, the response, and the human preference score. It can be, a score 0 or 1, 0 as the preference or 1 as the preference, depending on how you define the target. And in this case, we don't have the target, or the ground truth data set. So the goal for this reward model is to learn the loss function by the human preference. And that loss function will be expressed as the reward score back to the base model and fine-tuning process. The last part of the overall pipeline is the optional supervised fine-tuning. Let me explain. So if we don't have this part, if we don't have the supervised fine-tuning, and we just kick off the reward model training or the reinforcement learning process, you might be finding your agent or your policy or your base model hard to converge because there is just too many ways, and each signals we're giving the foundation model is tiny, is small. It's all the nuance. So it is better to prime your model with actual information, right? Again, the reinforcement learning is pretty heuristic. So you need to use supervised fine-tuning to prime your model with prior knowledge. It can be the domain-specific knowledge, the updates, the ground truths that you want the model to know. Then we use the we use the reinforcement learning with human feedback to further align the model output to the human preference. You are able to analyzing the friction point of your GenAI application, whether or not it is the prior knowledge or it is the last bit of human preference to further align your model output to a particular style, right? One thing I want to mention, but I won't have time to cover in this session, is we have a method called auto side-by-side to help you compare your RLHF model with the supervised fine-tuning model. You can actually use supervised fine-tuning to build your adapt layer and save the model checkpoint. And then you can optionally choose to use RLHF to tune the second version. And then you can use the auto side-by-side to compare the two models to see whether or not those additional steps will give you incremental benefit of keep improving your model. The last thing I want to mention is that on contrary, RLHF actually requires much smaller data set. By our experience, you just need to provide 1% to 10% of the original training data to the RL process to further align the results to the human preference. And we are seeing around 20-30% incremental increase of the model performance on some particular task. I think that's the last slide. So again, I probably will jump into my Cloud Console very soon, but here we go. This is again the RLHF pipeline inside of Vertex AI. I will be showing you a live demo very soon. The example code is pretty much like you probably already saw this in my previous demo. Maybe it is better. So, okay, so the data set. For distillation or building an adapt layer, the data set format is pretty similar. However, for reinforcement learning with human feedback, the data set is different. The input text is the prompt. Remember to keep all the instruction information, the particular prompt template, consistent to all the input data set, right? You cannot have variance of prompting template in input data set. It will confuse the model. And you will be providing candidates for the model to learn. The candidate can, you can put actually more than 2 candidates, but here is just a very simple example. And then you need to tell the model like which one is the human preference. With that all in mind, the prompt dataset will be, the evaluation dataset will be the same input prompt, as I mentioned before, with the same template, with the same instruction as your preference dataset, and then you can test the output of your tuned model. I'll be jumping into my demo. Just notice the time. Okay. Let me zoom in a bit. So yeah, again, you can get this notebook either from GitLab, or if you go into the model button, you'll be getting the same notebook when you find the foundation model, right? So for the foundation model, I think if you search for feedback, it will list all the model that you can use reinforcement learning with human feedback pipeline, right? I choose Llama. In here, browse the notebook, choose the one you want to open. Once you open this, it will automatically open CodeLab Enterprise. In here, you run this notebook as it is. Be aware that all the hardware requirements, you don't want to end up having a big bills of your cloud project. And then we have much more parameters to set. Just because it's a very complicated process, we are essentially training 2-3 different models. You can have a read of all these configuration. I don't have time to go through everything. But in here, this is telling you how you are calculating the training steps. Just because we are providing you different hardware capability, the batch size need to be aligned with the compute resources that you are choosing, the batch size, and then the learning rates, the iteration, all need to be adjusted. If you run this notebook as it is, it will work. But if you want to do further experiments, just change this data set. The documentation will have all the information you need. If we keep going down, again, set up the cloud storage bucket for your model interim output checkpoint, set up the service account. Service accounts need to have the right access to a cloud storage, have right access to the AI platform in order to create the pipeline, in order to create the metadata store. And at the very end of it, I just want to show you the configuration of the reinforcement learning is much more complicated. And I do recommend you to play around with each of these parameters. Those are, again, just example from outside, and we are using a particular template, right? We're just setting up this pipeline to accomplish a very simple task. So do experiment a bit in here. There's no guarantee. Your model will be definitely improved if you run reinforcement learning pipeline or if you run just a normal adaptive tuning pipeline. There's no guarantee you will be improving your model quality. But with experiment, with a lot of trial and error, you will be slowly seeing where exactly you can be improving your model and what type of training data you need to prepare for your pipeline, right? So again, I just show you the round pipeline. Let me just go to the pipeline. Okay, the pipeline in here. So I do recommend you to try Europe West 4. Apparently, they have more compute resources you can use. So you might have better luck when you want to locate some GPU or TPU in there. It's a fairly complicated pipeline. It's too big. I don't think you can actually see it. I do recommend you to run it. It's more complicated than any of the pipeline we have seen before. But there are a few things I want to mention. Here, the reward model trainer. As I mentioned, the reward model is the model that's gonna, decouple or understand the human preference and will be providing the signals, the alignment information to your base model, right? And once you kick off the reward model trainer, it will train the reinforcer. Actually, we will be saving. I think we will be caching the reinforcers checkpoint in somewhere. You can see all the input parameters and output parameters in here. Yeah. So the output adapter path and the model path are all in here. It's all saved in your cloud bucket. You can either explore this one, or you can, if you want to run an auto side-by-side comparison, you can choose the output model checkpoint, or if you want to keep, building another reinforcement learning on top of this particular tuned model checkpoint, you can also do that. And if we want to see the metrics, we're actually caching a lot of TensorBoard metrics. In the TensorBoard metrics, I didn't really have time to set up my TensorBoard, so I cannot show you, but if you click this one and all the information is saved in your cloud bucket, you can easily browse all the information you need. You can just import this information into your TensorBoard. You can have a view of how the model is converging. Actually, if we move back to the notebook, there are some visualization that you can see in the notebook. Right. Again, once we have the reinforcer being trained, you can deploy the model and run the inference pipeline. The inference pipeline is, again, fairly complicated because we need to have the base model metadata, and then we need to have the reinforcers weight loaded as well to kick off the tuning. Right. So time-wise, how did I go? Let me just check the time. Right, cool. I have a few additional minutes of this. Maybe I'll just show you one more thing in here, which is quite interesting. So let me just go back to here. So if we go back to the model garden, if you want to see which model that we are providing you the pipeline support, you can actually filter by the feature, right? So with the notebook support, you don't necessarily need to go to the GitHub repo to find all this notebook. Actually, if you filtered by the notebook support, you will be seeing all the model that we are providing you a notebook example to start with. One interesting one is, I think we are providing you this one. So this is actually the 2D to 3D vision model that we are providing. So this is a really interesting one. If you have a look at the notebook, you'll be seeing if you are providing 2D image, this fine-tuned model can actually produce a 3D image based on the 2D image that you are providing. Again, if you open the notebook, by default, it will open CodeLab Enterprise, but you do have an option to download this notebook, or if you want to import this notebook into your own workbench, it's a online Jupyter Hub. If you are familiar with Jupyter Hub, you might end up using the workbench instead of CodeLab Enterprise. I personally like the CodeLab because inside of CodeLab, you can use Duet AI as well. So that's a bonus point. So back to the model garden. If you want to see one-click deployment, you filtered by one-click deployment. So one-click deployment will be, again, it's more of the use case for the open source model like Llama 2, Stable Diffusion, or Misero. If you just click this, we have one-click deployment to help you deploy this model as it is in our model registry, and you can just call this model endpoint as it is. But our experience is if you just simply deploy this model, regardless if it is a Llama 7B or 17B, it doesn't matter. The performance is not as good, and you might be seeing a lot of latency. It's just because it's not as simple as have those pre-trained frozen weight of your model. It's all the optimization in the inference time. It's all the instruction tuning to a specific domain. That's why we're offering you, model in different sizes, in different variety, so you can choose the best one for your particular use case. For Llama 2, if you are just deploying as it is, we have few options. We have 7 billion parameters or 17 billion parameters. If you end up deploying this one, the latency is actually quite high, even though you are choosing, a high RAM GPU. It's just by default, those type of large model does requires a lot of infrastructure support. And the result is not as good as if you are simply prompting an our language model, which is if we go into the Vertex Studio and you go to language, you can try Gemini Pro in here. You can also try text Python 32K, or in here you will see you are experienced by yourself that a bare bone foundation, vanilla foundation model versus a tuned model, that's the power, that's the differences between just a foundation model versus a tuned one. Right. One last thing I want to mention is the pipeline support. It's a bit tricky. So in here, if you just filtered on the pipeline support inside of Model Garden, you'll be only seeing Llama 2, T5 Flang, or BERT. But actually, we are offering you much more pipeline template inside of the pipeline template gallery. So if you go into pipeline template gallery, you'll be seeing a lot of examples for Vertex AI. If you go to Vertex AI, you'll be seeing for the large language model text generation, we have a pipeline. We have pipeline for reinforcement learning with human feedback. If you open the pipeline, you can actually create, you can use this template to run multiple foundation models. So in here, if you don't want to use CodeLab again, you can always run this template as it is, and you just need to pretty much make sure that you are preparing the right data set. In the model configuration, you are pointing the right base model. Again, the base model has to be downloaded into your own cloud storage, so you can provide the base model URI in here, and set up the parameters, and then set up the learning rate, the target sequence, all that, and then you can kick off the run. Again, it's I personally tested on at least 3 or 4 different model variation. It all works with a few variants of how you're preparing your training data. But as you can see, when you are running this model, and if one of your pipeline actually failed, it's easy to identify where is the problem. Let's say we go to this one failed. You can see exactly which part it is filling. So this one, it fills, and then I can go into the log and debug the issue in here. You can even write the query to filter this into a particular time frame. Or in here, you can see, you can even compare the input and output, the summary. Normally, it is because of the input dataset or the output dataset is not correct. That's my own experience, but sometimes it's with the infrastructure constraint as well. Sometimes you fail to load some of your slave node, and some of the node having issues, so your pipeline might be failing. All right. How is time-wise?
We're almost on time, so thank you for this additional couple minutes too. Before we go into Q&A, I'll give you a couple of minutes to take a stretch, take a glass of water, maybe reset for a moment, and so we'll see each other in like 2 minutes, I think. With that, I wanted to once again. That's going to be probably a 10th time already in Startup School, but recommend our Google for Startups Cloud program. I saw already a lot of startups trying to get credits and more from Google for Startups Cloud program. All the details are under this QR code over here, or Google/cloud-program. That's one. The second part I wanted to get your attention to is, of course, the feedback. The feedback is a gift, as some of the people say. And of course, we would love to know how our this week's instructors did. If you have any also suggestions about how we should proceed with the next editions of Startup School, it's also a great place to let us know. So if I can ask you to grab your phone, scan the QR code, or just type this URL in your browser, I would really, really appreciate this. On Monday, you'll get, again, our typical weekly recap with this link, but we would love to know almost now. Last information from my side. I know it was a fairly technical and complicated session. I hope you all were able to follow. Remember that practice makes perfect. So the notebooks that Catherine was showing us, you can, of course, access them through Google/GenAI-Labs. They are both listed over there. So I think it would be worth, practicing a little bit, checking if they are fine, if you understand everything, and maybe, just maybe, rewatch this video on demand if something was not clear. But with that, we just have a couple of minutes left today. It's the end of the week 5. So I would love to invite Catherine back and talk a little bit about the questions from the audience. I mean, Catherine, first of all, just to reiterate that, there are a lot of great models out there in the world, created by a lot of different companies, and we have introduced the idea of embeddings. We have introduced RAG. Now we're talking about tuning and this reinforced learning. But why can't we just use some of the things out of the box? And so the first starting question would be there's a lot of startups out there with a lot of different needs. When startups need to consider tuning or reinforced learning, and when they should just go with the models that are there, ready for use out of the box, plug and play almost.
Yeah, that's a great question. I think for startups, I would always recommend, because speed is the key, right? You want to really capture the momentum. You want to capture the critical moment where you see a gap or a true demand from the market. And quickly prototyping and building something as MVP is always critical. At this point, I don't really recommend you, unless you are building a foundation model, right? If you are building something more personal, like a virtual girlfriend, rather than ChatGPT. I'm just giving you an anecdotal example. Then you probably think of tuning the foundation model is critical. Otherwise, if you are just building an application, abstract layer on top of those vanilla model, then feel free to use any model that is available. That's why inside of the model garden, there's a lot of options for the open source model. Actually, if you go into Hugging Face, you'll be seeing on the leaderboard, it's all the open source model tuned by different university or startups. So start with that. And once you have more information, like the golden data or human preference, you have the human interaction, you have additional information, then think of tuning. Is that a fair explanation?
Absolutely, I buy it, and I love the example of the AI girlfriend or chatbot. Valentine's yesterday, yes, we are in the mood.
Oh, that's a bit pathetic too. I do love the movie Her.
Oh yes,
That's
that's
cool,
true.
yeah.
That's true. That's true. We have two questions related to supervised fine tuning. So let me read them out loud to you. So Quentin Collette is asking, in supervised fine tuning, what happens if the knowledge in the data set conflicts with the knowledge that LLM already has encoded? That's a really great question, I think. And I also think that when you actually need fine tuning, when you need reinforced learning, when you need add your own data sets, it's because that LLM might get other things wrong. So what happens if this knowledge is in conflict?
It's interesting. It's a really, really good question. It's hard to identify. If you can give me a much more granular example, that would do. I would just give one example from my side. Let's say I'm Aussie, so I'll give you an Aussie example. So actually, I'm working with one supermarket in Australia, and we are building this chatbot solution for that company. And guess what? In Aussie, I think there is a term to describe a particular biscuit. It's like a dojo momo or something. So that's actually describing a particular biscuit, all the Aussie knows. However, the model cannot understand. It's not so much of a conflicting information, conflicting knowledge, but additional knowledge to the model. We try supervised fine tuning, like it can just align the model output to certain ways. However, we struggle to add those additional knowledge into the foundation model. Because if you think of foundation model, the only way you can bring in additional knowledge is to change the frozen weight of your foundation model. That's why, model, the offline model, we're always struggling in getting new information from the world. That's why we need to keep releasing. We need to keep continuously train our model with additional update from the world. That's the additional knowledge inside of the foundation model. Supervised fine tuning will have limited power in adding those new knowledge. It doesn't matter if it is a conflicting knowledge or it is just updating some of the existing knowledge inside of your base model. Supervised fine tuning is just adding additional preference. It's like telling the model how you should be behaving on this particular task, like summarization, like identifying something, rather than changing the knowledge, if that's a fair explanation.
I understand this. Additional one from Ramon, because we're talking here about supervised fine tuning, and Ramon is asking, is this just a one form of adapter tuning? Because the term supervised fine tuning assumes that there's also an unsupervised fine tuning. And of course, we wouldn't like to have the all AI being unsupervised. That's a great plot for some sci-fi catastrophic movies. But all in all, is this just a form of adapter tuning, and whether any kind of unsupervised fine tuning exists?
Yeah, so go back to the basic concept of machine learning. When we say supervised, it just implying that when we are preparing the training data set, we know the target. The target can be, I want you to summarize this information, or I want to extract certain information from this conversation. You know the target. You know exactly, I want to extract the user's name, I want to extract the age. You know the deterministic answer, so you're preparing the model with the target. So that's supervised. Like I'm supervising you by giving you example. This is exactly what you need to do. However, unsupervised is telling you that I don't know the answer. Unsupervised, not fine-tuning, unsupervised learning is used primarily in building the foundation model. So how does the foundation model learn the word knowledge? It's by giving a lot of information to the foundation model, and you learn your own knowledge. You build your own embeddings and nuances information, like you're building your own vector space to understand the semantics relationship in all the information that I'm giving it to you. It is like unsupervised is only useful in the pre-training part, not in the fine-tuning part. So that's the caveat. And supervised and unsupervised is just the way to describe whether or not you know the answer, you know exactly what you are expecting from the model or not. So it's a mix and match. But normally when we are saying tuning, it is supervised fine tuning. It's just a term.
I think we have just time for one more question, and my moderators are sending me this one from AJ Lalu. Are there precedence rules applied between adapter layer versus foundation model? What happens if they would have produced different outputs on their own, contradictory perhaps? AJ is asking.
Yeah, it's a really good question. I laugh because it's not as simple as those two things are producing two different things. When you think of a model, a base model is a neural network, and inside of that neural network, you have multiple layers. You have like let's say 5,000 or 50,000 layers of small nodes. And what happened in building the adapt layer is in one particular layer, I'm just adding those few parameters in. The parameters itself, the adapt layer, wouldn't provide any meaningful information. If that makes sense, because the adapt layer by itself is just a few floating points. It has computational meanings rather than the real world meaning. So the adapt layer by itself wouldn't be providing you any meaningful result. But the power is with those few layers, I'm changing the numeric number in between those neural network when it passing through. I'm changing it slightly. That will have a big impact in the final output. So that's the power of the adapt layer, not necessarily like, the 10 more parameters that I'm tuning, but produce a completely different output. Yeah, it has more numeric meanings, mathematical meaning, rather than like a real world knowledge.
We're on time, and let me just quote a comment that is there from Matthew. Outstanding session, really great, many thanks. I can say absolutely the same. Outstanding session, really great, many thanks. Many thanks to you, Catherine. Thank you for being with us. Our AI experts are trying to answer more and more questions. It's usually that towards the end of the sessions there are more and more. So you will probably get answers to yours, dear participant of Startup School. Catherine, once again, thank you. I hope we will see you in the future editions of Startup School. But for now, that would be all. When it comes to the week 6 and the next session of Startup School, we are seeing each other next week for the week 6, the last week of Startup School. We're going to see each other on Tuesday, February 20th. And we're going to talk about model evaluation for Gen AI. We're going to have Ivan, our customer engineer. We've been working with Ivan on previous Startup Schools as well. So I can highly guarantee that it's going to be a good one. You saw the feedback. Once again, I will bring this slide over here. You can leave the feedback for all the sessions from this week, so Tuesday and Thursday. We're gonna see each other next week, so please come live, please watch on demand, please finish the homeworks, but for sure I'll see you next Tuesday. Thank you very much for your participation. Bye.